Hey everybody, welcome to the webinar. My name is Marcus with MLC CAD Systems, and today we're going to talk about sheet metal. I've got a nice little sheet metal manual here. If you attended one of our live events, you got one of these. Everybody here will get a copy of a PDF copy of this, as well as any files so that you can reference those and take a look at them. But today what we're going to do is go through just a simple sheet metal example to talk about sheet metal. Specifically, we're going to talk about more than just sheet metal in SOLIDWORKS. We want to talk about communicating with the shop, working inside of a business, understanding the terminology, basically everything that would go along with sheet metal training that you might have questions about, from getting started all the way through being a pro. Those are the kinds of things we want to discuss today. Ask questions as you go. Type in the comments when this goes up on our YouTube or something like that. Feel free to ask questions there. But I'm going to build this sheet metal toolbox. This toolbox was built by, and we still have it, he still has it, Roland Robles in our Dallas office. His grandfather did this with him when he was a kid and helped him to kind of learn fundamentals of working in a shop and working with sheet metal. So it's just a really simple example, but it does a nice job of giving us something that we can work with and kind of host this discussion about. So I'm going to create a brand new part, and we're going to go ahead and build out this toolbox. So the first part I'm going to build is the tray. And if you think about the tray kind of from the right side, you can see that U-shaped tray. So I'm going to start a sketch on the right plane, and we'll come in and draw a line. Now for this line, this is going to be symmetric, so I can do a midpoint line, which is kind of a slick way to do a line with symmetry. And we'll go through and we'll add some dimensions to fully define this. So this is going to be my width, and the width is 8 inches. But more specifically, the width is D1 at sketch 1. And that's not very helpful. I'm going to be able to make different sizes of toolboxes off of this one model. So I am going to spend quite a bit of extra time kind of adding documentation. I'm going to call this width, if I could spell. And now, instead of it just being D1 at sketch 1, it is width at sketch 1. So we'll come back and use that a little bit later, you'll see. For the height of the tray, we're just kind of using this as a standard. We're always going to say that it is equal to half the width. Now if this was Excel, I would just type in equals, and then I'd go click the cell I want it to be equal to divided by 2. And same thing goes here. Equals width divided by 2, click OK. Now we have a formula. And that formula is controlling the size of this, and if at any point I was to change the width, this height value is going to update automatically. Draw one more line, and we've got ourselves a fully defined sketch. Alright, first thing we'll do is do a base flange tab. So the base flange is kind of like the extrude boss of sheet metal. If it's an open profile like this one, it's going to add thickness to the sketch and just extrude it out away normal. Always pay attention to where your thickness is being added. In this case, my thickness is being added to the inside, and that's good. These are my outside dimensions. If I flip this to the outside, now those dimensions were my inside dimensions. Sheet metal typically ends up being a game where you mess up by a variable equal to the thickness or the bend radius or some combination thereof. So 30 thousandths is our thickness, 30 thousandths is our bend radius. We're keeping this really simple because we're just kind of playing around with this, but normally I would use a gauge table. And if this is you going to a company working with SOLIDWORKS and you don't have a gauge table for your company, go in and grab the one you would use or the one you find to be most useful. Save a copy of it, and then just clean it up. Add only the sizes you guys generally like to use, the K-factors and bend allowances and stuff like that that are important for you, and that's going to save you a lot of time as you go. For now, I'm just going to leave this K-factor 0.5, tear relief, and I just want to say for my direction, I'll do mid-plane, and we'll do 12 inches, and that is my tray. All right, so now I've got my base flange feature. I've got a couple other features we'll explore here in the feature tree as we go. But let's add a few more features to this one. We're going to add some flanges to stiffen this box up. So Edge flange, just click an edge, move it out, and drop it. And then you can continue clicking any other edge. It doesn't really matter which side you click on, top or bottom, because it assumes you're bending them all in the same direction. If you want to flip any of them, you can. Just flip the little arrow, but it does a nice job of kind of predicting what I want, giving me these nice mitered corners. I can change the gap if I want to on those corners. For the flange length, this is something I want to standardize. So I'm going to say equals, and I want to set it equal to a variable. And I don't have a variable yet. I can go into the equations dialog and set one, but if I just type in a F, like the F for the flange length, I can then create a global variable. And what that does is it links anything that links to that variable is now going to have the same value. And I can change it from anywhere. So later on down the road, if I say, you know what, I'd like it to be 3/4 instead of half, I can very quickly make a global change to my entire sheet metal part, and all flanges will update. Last thing is the flange position. Do I want to make this part bigger by adding these bins? And the answer is no. I want the flange material to be inside, meaning don't overall change the size of the part. So it's going to go kind of push it back and then add my flange so that the overall length stays exactly the same. So base flange, edge flange, these are pretty standard things, kind of your bread and butter of working with sheet metal. Now the next part I want to do though is going to be an end cap, and it's going to be a separate piece. Now you could do this in a separate part, build it as an assembly, but I'm going to show you how to do this with a multi-body. So with a multi-body, I'll just come in here and create a sketch for my next part. The shape of this at the bottom matches the shape of the tray, and I've already drawn that. So instead of redrawing it, I'll go ahead and select the sketch and just hit Convert Entities. And what that does is it just brings that sketch into the active sketch, and then I can kind of finish it out from here. So let's do this. Let's just kind of, not really to scale, but we'll grab and fully define this. The width up here on the handle, I want that to be 3 times the flange. So I'm going to say equals global variable of F times 3, and that's just how we like to define or just, dimension the handle size. Then we come in here and say these 2 lines need to be equal. And last but not least, we'll set the height. For the height, let's do 7 inches. That should work out pretty well. And now we have a fully defined sketch. Base flange tab inside sheet metal. This is a closed profile. Previously it was an open profile. So instead of adding it to sort of the thickness, it's going to extrude the whole thing like an extrude boss, and it's going to extrude it the thickness of the thickness of the material. This is kind of pushing into these flanges, and so I need to go ahead and reverse the direction so it pushes out instead of interfering. And I also need to clear the merge result checkbox. So if I wanted to add a whole bunch of extra material onto one of these flanges, I could do that, draw on the flange and just say merge, and it just becomes a part of the previous part. But for this one, it's a whole new part, it's a whole new piece of a multi-body part. Click OK with merge result turned off, and now I have a cut list with 2 different bodies in it. So if you're used to a multi-body part, you'd see the bodies folder. A cut list is a little bit different because it has some intelligence. We'll see that when we start building drawings and such. All right, let's do another edge flange here. Just grab this top edge, pull it out, and our flange thickness is going to be F, or flange width anyways. And then for this one, oops, I jumped out of it too quick. I want to make this bend material outside. And the reason I want to do that is I want the handle to kind of come in underneath this thing. So now for the handle, oh, nope, not ready for the handle yet. I need to do these flanges to kind of hug around these corners. So we'll grab the edge flange, pull it out, grab these other edges. One of the biggest benefits of doing this as a multi-body part is the ability to establish clearance between parts. So if you notice, this one is kind of material inside, it's kind of hitting these other pieces. I want to do material outside so it wraps around, But even more than that, I want to set some tolerance, some assembly tolerance for this flange. And so to do that, I'm going to check this box that's called offset. And what I'm doing is saying, let me get like 30 thousandths of assembly clearance so that I can put this thing together, right, when we go to assemble it. And that 30 thousandths is going to be maintained. So if I ever change the width of the tray, the height, anything else, that 30 thousandths clearance of assembly all the way around is going to be maintained every single time. So definitely keep an eye on that. Looks like the flange offset was failed. Let's see if we try that one more time. It doesn't like the 30 thousandths because that's equal to the bend outside, so we'll just do like a 20 thousandths and we should be good to go. All right, a couple little more detail things. A lot of times people with sheet metal call up and they say, hey, my corners don't look right. Well, the corners in a flat part and the corners in the bent part are both important, but the flat part is what's actually going to get fabricated. The bent part is just a visualization of that. In reality, this is going to bend across no problem. But if you ever see an edge like that and you're like, I don't like how that looks, I want to change that, edit the feature, and that is the bend relief. So for this bend relief, I could say I want to do like a cut, right? Cut back like a notch or something here. I don't need a notch. What I need is to tear it, but I don't want it to tear just right there. I want it to actually kind of extend a little bit. And it kind of creates a little ramp there and just kind of cleans up that corner a little bit. So the flat pattern is still probably going to be what you want, but just pay attention to those little details. Depending on what that looks like in the folded or the flat configuration will determine what your result should be. All right, let's do a mirror on this. So for the mirror over the right plane, we're going to do bodies to mirror. Not faces or features, bodies. Because this is a multi-body part, we're going to create multiple pieces of the same part, and the cut list is going to recognize them as identical pieces. Even though this was mirrored, because it's symmetrically modeled, it is showing them as identical parts, and so it shows them with a quantity of 2 and groups them together. That's exactly what we're hoping for. For the handle, let's draw that on the right plane, and I'm going to grab this bottom edge. So this bottom edge right here is where I'm going to put my handle. So I'm going to use the convert entities command one more time, and it just converts that edge over to my sketch. This open profile sketch, something as simple as a line, can very quickly create a base flange. So we'll say there, and we want to make sure we add the material to the bottom. As we pick the bottom edge, we want to go down from there. And then for direction 2, we'll say also up to surface on the other side. All right, there we go. Last couple flanges we need to do on this one. Let's go ahead and add a flange down here so that I can stiffen this corner. Now this one, it might get a little bit difficult to see where we're working, so I'm going to hit the Tab key. Tab on your keyboard very quickly hides a part or a body in a multi-body part so that I can come in here and add my edge flange. This edge flange is going to be material inside with no offset. Pay attention to these parameters because they it's very much a detail-oriented thing, working with sheet metal and getting everything exactly the way you want it. If at any point in time you want to take a look and make sure you didn't mess anything up, you can do things like interference detection. Just like you would in an assembly, interference detection will help you find any interferences that you have. In this case, it found this corner is square because I forgot to put my flange on both sides. Let's just go ahead and edit that feature, and we'll add one more flange, and that should take care of that interference problem and keep us rolling along the line. All right, next flange we're going to do is more of an overbend. So with this edge flange, we're going to grab these edges and we're going to dimension these as 135 degree bends. and I want 2 of them. And then depending on the length, we're going to start to potentially have some problems. So if you take a look in your book to page 12, you're going to see that when we come in and we define these flanges, if you start to create something more like a closed-in box, you're going to have a problem where the die cannot reach inside there. And so what I've done on this one is for these two 35 or 135 degree bends, I modeled up an assembly of my dies, and I said, can I get my die into this bend region right here while this other flange has already been bent, right? We're dealing with order of operations, a very common issue with sheet metal bending. So in this case, yes, we can do that based on the configuration and the orientation of our part. We just have to make sure that the dies are installed the way they need to be installed for what we're trying to do, make sure the guys in the shop are okay with it. But this could potentially create some difficulties depending on the types of dies we're using. But this actually doesn't stop with just this corner being potentially blocked by this flange. This whole thing right here is going to be potentially problematic. So if I bent these 2 sides first, they would then get in the way of bending this flange on the end. So we have to do this flange on the end, then bend these guys. And when we do that, this top bend, or this top die that comes in to do this bend, is going to have to fit in between these ears. If you don't want that ear to be in the way, you would have to swip the order of operations, but of course we can't do that. We've already determined, and so you sort of start to get this issue where you're trying to map out which order of operations is going to be the best. For this one in production, I probably would take the option where I add some relief cuts to chamfer these edges so that the bottom die doesn't interfere. So I can have a continuous bottom die, a shortened top die, right? That's the exact size or width of this. And a lot of times you'll see at the brake press, you'll see lots of long dies, and then you'll see various different sizes of short dies that can be used to make up any of these random sizes that you might need to do. But another option you may want to consider is something like a 3D printed die. So 3D printing creates some very durable parts, and those parts can be used to do things like bend or form metal in low volumes. How many times have you had a situation where you want to bend something for a prototype, or you have a job and you need to make 10 or 100 of something, and you don't want to have to make full strength tooling or send it out to a CNC machine shop to do it? We can create a lot of tooling using 3D printed industrial materials and get a lot of things done. So some different options there. And on page 14, we talk a little bit about, you know, the costs and the ROI of something like that if you have that capability in-house. So let's go ahead and show everything else we've got here. Shift-Tab brings it all back. F to fit to screen. And we're now to the point where we could probably save this, and we're going to start creating some different sizes. So I'm going to call this my webinar toolbox. We'll save over top of that guy. This is our webinar toolbox, and I want to create different sizes, and I want to vary some of the dimensions in my sketches and features to get those different sizes. Now, if you remember, I started this a little bit, and then I kind of stopped. This dimension right here, this 8, that dimension right there is width at sketch 1. I renamed it width, but it's still called sketch 1. So I'm going to rename this. I'm going to say this is the tray layout sketch. And so now that dimension is called width at tray layout. If I keep that going, this base flange here, this base flange feature, I'm going to call that my tray. And then the tray length dimension, we're going to rename that as length. So now we have length at tray and height at tray layout, and then this one right here, this is going to be the height at the end cap sketch. And that's just going to simplify things that are going to happen next when we create, effectively, a product catalog. So configurations control variations of a part. And a lot of times you'll see a product that has different sizes, and we're going to actually create those sizes in here using Excel spreadsheet. So insert design table, and I'll click OK, and it's going to automatically create a design table and bring in all the variations that might be relevant for this design. The variations are the width, possibly the thickness, possibly the length, and the height of the end cap. And when I click OK, boom, we've got rows for all the part numbers, the product variations, and columns for all the dimensions that we might want to use. So I'm going to do this. I'm going to say small, medium, large. For the width, we'll do 6, 8, and let's say 9 on the width. For the thickness, we'll leave those all the same. Notice you can just drag and drop, copy, paste, put in formulas, whatever you want here, right? 12, and then we'll say 12 there, but the height will change. So we'll say 6 on the height, 8th, and then we'll just say 12. A really tall, weird, funky looking tray. Let's do like 18 here. Nope, 28. All right, so let's click away and let's see what that did. It should have created multiple different sizes for us that we can now utilize. And anywhere we have a toolbox, if somebody says that toolbox is too big or too small, you can simply change the configuration and show that other one. When you get to the drawings, you can create your drawing of your standard one, and then you say, well, now I need to make a drawing of the large one. All you have to do is change the configuration on the drawing, and now you've got that same drawing in a large version. So really simple and easy. I did a little bit of work up front because I knew that this thing was going to be something that I'd want to modify later or work with later. And so that's where I created some of these equations, global variables, and that design based, or that design table in Excel. All right, let's start talking about documentation for manufacturing. First thing I want to talk about is flat patterns. So we talked a little bit about this flat pattern and how the flat and the bent part are effectively two different designs, but they're very similar. They're related. The difference between them is that one of them is bent, obviously, but then the other one is adjusted based on certain factors. Okay, so we'll take a look at page 19 in this workbook, and when you bend a sheet metal part, right, that sheet metal part is going to stretch just a little bit. And when you flatten it back out, or unbend it, I guess would be the more appropriate way to say it, you're going to have to account for how much of that stretch is taking place. And so because I made this part in the folded shape, the flat pattern is going to be adjusted based on how much stretch I expect there to be. If I'm expecting a lot more stretch, the flat pattern will actually be smaller. If I'm expecting less stretch, the flat pattern will be bigger. And the way we calculate that in SOLIDWORKS is usually with something called a K-factor. Now, you may have heard bend allowance, bend deduction, setback, things like that. Those are really great for back-of-the-envelope calculations. Right? If you're trying to build a section of C-channel and you want to know how big to create your raw piece, those bend allowance calculations make it easy to just say, boom, 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 add them all up, call it good, that's the size I need. But when you start to deal with situations where you have lots of bends compounding on each other, maybe you have some overbends or underbends, you got different angles of bends, different thicknesses of material, those bend allowances only apply to one combination of material thickness, bend radius, and angle, bend angle. So it's a lot of manual work to do anything other than 90 degrees on standard materials. So the way K-factor works is, if you look at that diagram, you can think of the inside bend radius is under compression. And the material there is going to compress, and that edge on the inside radius is going to be shorter because it's compressing. The edge on the outside is stretching, so the outside edge is going to be longer after it's finished bending. but somewhere in the middle is a neutral axis. That's where it no longer stretches or compresses. It's right in the middle. And if you draw a line very carefully down the thickness at a certain ratio through the thickness, then that line represents the shape or the length of the flat pattern. And so that's typically what we use, and K factor of 0.5 is relevant when you have things like paper. If you're going to bend a piece of paper and it's going to have a bend radius, it's not going to be a crease. When you unfold that piece of paper, it's not going to be longer because you sort of rolled it a little bit. That's a K factor of 0.5. No stretch, no compression. It's just going to bend and give you equal compression and tension. And that's true for really thin parts. It's true where the bend radius is at least 2, maybe 3 times the thickness of the material. So like we worked at a shop where everything was 16 gauge, so 1/16 of an inch, and all the bend radiuses were 1/8 of an inch. And so K factor worked out fantastically in that scenario. You also have situations where you have bending really thick material, or perhaps you're bending it really sharp. That's where the K factor starts to drop. You'll start to get into the 0.4, maybe 0.3 range on a really, really thick part. But here's the kicker. It depends on your machines. It depends on your materials. You can't really predict it very well. The best thing you can do for your shop is to take a sample part, just a piece of material, measure it very carefully, and then bend it. And then measure that. And you'll come in here to SOLIDWORKS Sheet Metal, and you'll create the same part, and you'll make it flat, and you'll make it bent. And then you'll measure those two, and make sure that the K factor gives you an accurate flat to bent, connection or correlation. And at any time, if you need to make a change to that, you can come into the sheet metal toolbar or feature here and change that K factor from 0.5 to whatever else you need it to be. And each part can have a separate K factor. So you can have a K factor for each individual piece. You can have a K factor for each individual bend. And then when it comes to the flat pattern itself, the flat pattern has some additional information you can modify to control how this thing works. So SOLIDWORKS Sheet Metal is doing a lot in the background, kind of the accounting work of making sure your flat pattern is going to be accurate, but it is up to you to make sure you put in the right parameters to be able to build that. All right, let's make a drawing. So for the drawing for this one, let's go ahead and use like a B-size print. And for the first sheet, and you can do these on separate sheets as you need to, but on the first sheet, I'm just going to come in and create almost like an assembly view, right? The whole part, this toolbox looks like so. Drop in my views. I want to show how many pieces are included in this, right? Because I got 3 different pieces and I want to detail what they are. For an assembly, you'd create a bill of materials. But for sheet metal, or this is also true for weldments, you would make a cut list. And a cut list takes that cut list information and puts it in table form. All right, so right now, this isn't very useful information. We've just got sheet for the description and length is blank. Let's go take a look at what this looks like in the part file. And what we can do is go into the properties of these cut list items. And here is the description. It's called sheet. Now this works really well if it's like a 2x2 by 1/4 inch wall, steel tube. But for this is my tray. That's my description of the tray. This one is the end cap. Notice it highlights in the background which part is which so that I can very quickly go through and identify my pieces and give them more descriptive names. The information, things like bounding box length and width, is all in here as well. And so what I can do now is go back, and the description is changed, but I can also come in and change these columns. So the length, that's more appropriate for like a piece of structural steel cut to length. I'm going to say bounding box width, and then I'm going to insert one more column and call it bounding box length. And now my purchasing team can use that to very quickly look at about how much material is going to be required to build this thing. I can add my balloons. And for the balloons, you know, they're just like you normally would expect. They're very intelligent, and they're going to automatically show you what each part is. All right, so let's create another sheet, because what I want to do is create a view of the flat part as if it was by itself. In other words, I don't want it to look like it's part of a multi-body or an assembly. I want to select a body. We'll grab just this one piece right here and say, I want to create a flat pattern view of just that one piece. And I come out and drop it into my drawing, and it creates that view, and it creates all of the bend lines, the bend notes, all the information necessary to fabricate that. I can add my shapes in the bent, and then I can come through and add my dimensions. Now, talk to your shop about this. Depending on how they set the backstop on their brake press, they may want dimensions like this over here on the flat pattern, or they may want dimensions here directly on the part itself, kind of the overall, you know, outside to outside dimensions. A lot of times your CNC brake press, if you have a CNC, is going to calculate that, back calculate that for you from that dimension. But the key is communication. Make sure you're giving the information, the types of information that everybody needs, when they need it and where they need it. All right, so these flat pattern configurations are being created automatically by the drawing. So when you create a drawing view of a part that is flat, it creates a flat pattern configuration. So if you were to open this up from right here, say open part, this is a pretty common tech support case we get sometimes, where you open it basically in the flattened configuration. So if you go back to the default configuration, everything's good to go. But if you're in the flattened configuration and you unflatten it, now your flat is no longer flat. So just keep that in mind. When you're working with sheet metal, every flat pattern view you create creates a derived configuration, and just make sure that you're not messing those up. The flats should be flat, the default should be bent, and then all your views and everything should sort out the way they're supposed to. Now I need to send this out as a DXF to a laser, right? We could cut this on a laser, water jet, plasma, EDM, punch. A lot of information here in the book about different, you know, pluses and minuses for each approach, for each type of technology. But at the end of the day, I need a one-to-one outline of each of these parts exported to where I can send it to my shop. Instead of saving a drawing, like making a one-to-one drawing and saving it out and clearing out the title block, which is what we used to do about 20 years ago, I'm going to say export to DXF, and it's just going to automatically create that for me. So we'll say save as, and I'm going to have it, we'll just save it there, that's fine. I'm going to have it save not faces, which by the way is a cool feature. You can export a face directly to a DXF. But I'm going to say I want to export sheet metal, and I'm going to export these 3 sheet metal parts. And when I export them, I want to export the geometry and the bend lines and any sketches. Now these sketches, this is where you might put in like a scribe layer, right? You may want to scribe your bend lines. You may want to scribe a logo or some targets for drilled holes later, or locations for some things. Right? Maybe you want to document where you want your spot welds to be. You could scribe a little X or something like that. Right? Everybody's got their own way of doing things. If you want to put that in there, you can. I'm going to say I want to put them in as separate files, but I want to be careful about how that gets exported. Well, the jobs that I worked at that had sheet metal fabrication in-house, when I exported the wrong scale, they brought me the part at the scale I asked for. It looked like a keychain, basically. And so that part was obviously not one-to-one. This is going to force it one-to-one, so it's always going to be true size. But this mapping layer allows me to say, hey, I want to define certain layers. I want a scribe layer with blue lines, bend layer with red lines, and then I want to map my entities from SOLIDWORKS over to these different layers, so that when it gets to the shop, the layer mapping is set up correctly for whatever it is that their software likes to use. So that map file is something you can create and utilize anytime you want. The last step it's going to do is offer me the last option to clean up my sketch or clean up my flat pattern in case there's something in there they don't want to cut. Typically, if I do like a tapped hole, right, it's going to show the pilot hole in the flat pattern, and I don't want to cut that pilot hole there because it's going to harden it using the laser, harden the edges, and then it's going to break my tap. So I can come in here and select things I don't want and just get rid of them, or I can come in and just delete that guy, whatever I want. Let's go ahead and hit save, and that saved out all of my flat patterns as DXFs with layers ready to go. Hopefully you found this useful. This event, we put this together specifically to try to just educate you on what else is going on. We're going to do 2 more webinars. We did one already on flat patterns with Mastercam. Everybody's going to get a link to the page where this webinar, you can re-watch it if you want to. You'll also be able to download the PDF file of this book. Go ahead and ask your questions anytime here in the chat. We'll take a look at them and kind of do a Q&A, but for now, let's go ahead and turn it back over.